Continuing our discussion of the circularly polarized light, in part A we have calculated the closed path integral E dot dl, in part B the magnetic flux through this loop P. Now in part C, use Faraday's law and the relationship omega over k is equal to C to determine B in terms of E and C. Now using Faraday's law, I can calculate the induced EMF. Epsilon is equal to minus d phi b dt all right. And if I look at my answer here, if I take a time derivative, I will obtain an omega. The sign will turn into a cosine, and there's a minus sign here. So a minus sign and minus sign will become plus. Then I will have BH omega over BH omega lambda over pi cosine omega t. But if I note that I have k is equal to 2 pi over lambda here, so if I multiply the top and bottom with 2, I can see that this is actually 2 BH omega divided by k, where k is 2 pi over lambda, cosine omega t. Now, the problem reminds us that the speed of light, c, is the ratio omega over k. So this is omega over k. So looking at the induced EMF I have calculated here, epsilon is equal to 2BH omega over k is c cosine omega t. And now if I go back to my answer in part A for the induced EMF, closed path integral E dot dl, 2EH cosine omega t, this must be equal to 2EH cosine omega t. So that's the answer from part A. I can see that this implies B is equal to E divided by the speed of light, c, as suggested. Okay, so two alternative ways of calculating the EMF, closed path integral E dot dl, and the magnetic flux. From the magnetic flux using Faraday's law, I obtain the relationship between B and E to be B is equal to E over C. Part D. The wave specified above is right circularly polarized. We can describe left circularly polarized light by swapping the signs on the two terms that involve sign functions. Superpose the above wave with such a reverse polarized analog. Write expressions for the electric and magnetic fields in that sum. Note that the result is a linearly polarized wave. Okay, so let's see. We have, for the right circularly polarized wave, electric field given as a function of z and t in the problem statement as E cosine kz minus omega t I hat plus sine kz minus omega t j hat. And for the right circularly polarized wave, the magnetic field as a function of z and t is given as B minus sine kz minus omega t I hat plus cosine kz minus omega t j hat. Now the problem statement says switch the signs of the sine function. For the left circularly polarized wave, the electric field then will become E cosine kz minus omega t I hat. Now instead of the plus sign here, I'm going to have a minus sign, minus sine kz minus omega t j hat. And for the left circularly polarized wave magnetic field component, I will have B. Instead of the minus sign here, I will have a plus sign, plus sine kz minus omega t I hat plus cosine kz minus omega t j hat. Okay, so I note here that these two terms are for right circularly polarized and these two terms are for left circularly polarized. Okay, so I have obtained the corresponding electric field and magnetic field components. Now I'm asked to add the right circularly polarized electric field component with the left circularly polarized, superpose these two waves. And now what happens here? The sine terms will cancel. I will obtain 2e cosine kz minus omega t in I hat direction. So this gives me 2e cosine kz minus omega t in I hat direction. And for the sum magnetic field, here I'm adding the right circularly polarized magnetic field component with the left circularly polarized magnetic field component. One has a minus sine kz minus omega t, the other one plus sine. The signs will cancel. I will obtain two cosines in the j hat direction. So this is 2b cosine kz minus omega t in j hat direction. So that's the answer for the sum, superposition. Now you can see that we have two waves in phase, two traveling waves in phase. One is in I hat direction, the other was in j hat direction. The wave propagates in I hat cross j hat k hat direction. This is describing our familiar linearly polarized. So this is the linearly polarized electromagnetic wave, as suggested by the problem statement. Let's look at the last part of the problem. Consider right circularly polarized green light with wavelength 500 nanometers and intensity 100 watts per meter square. What are the values of E and B? Hint, determine the pointing vector. Note that this is constant. Its magnitude is the intensity of light. This is something we actually know. All right, so in part E, I'm looking at the right circularly polarized wave. So let me rewrite the right circularly polarized electric field component, Z and T. It is E cosine kz minus omega t I hat plus sine kz minus omega t j hat, and the magnetic field component as a function of z and t is be minus sine kz minus omega t I hat plus cosine kz minus omega t j hat. And I'm given the wavelength of the light, green light, is 500 nanometers. The intensity is 100 watts per meter square. Okay, the Poynting vector S is 1 over mu 0 permeability of free space, the cross product of electric field with magnetic field. So if I perform this cross product here, I have 1 over mu 0 EB. So I hat cross I hat is 0, I hat cross j hat is k hat. So I will obtain cosine square kz minus omega t in k hat direction. J hat cross j hat is 0, but j hat cross minus I hat is going to give me k hat. I hat cross j hat is k hat. J hat cross I hat is minus k hat. J hat cross minus I hat is k hat. So this is going to give me plus sine square kz minus omega t k hat. Sine square plus cosine square k hat, that's 1. So this is just EB over mu 0 in k hat direction. EB over mu 0 in k hat direction. And we know that E is equal to B times C from part C of the problem. Okay. So we can see that if we write E is equal to BC, B squared C over mu 0, our Poynting vector magnitude, is equal to the intensity. So B is equal to I mu 0 over C square root. Now, the magnitude of the Poynting vector is the intensity of light. So that's what is mentioned here. So basically, that's what I have done. Magnitude of the Poynting vector is the intensity. But it's not the average in this case. So we're talking about the actual intensity, not averaged. The electric field, on the other hand, can be written as, because E is equal to BC, intensity mu 0C square root. So substituting the numbers for these, let's take it to the left side. For the magnetic field B here, we will have intensity is 100, 4 pi 10 to minus 7 divided by the speed of light, 3 times 10 to 8 meters per second. We take the square root. All right. This is going to give us a magnetic field magnitude 6.47 times 10 to minus 7 Tesla, or we can write the magnetic field as 0.647 microtesla. On the other hand, E is equal to B times C, so that gives me electric field magnitude 194 volts per meter. Normally, remember, we talk about average value of the Poynting vector. So in that case, the magnitude of the average value of the Poynting vector is E max B max. So E max squared over 2 mu 0 times C here. So it is C times the average, the energy density. But here it's not talking about the average values. So it's talking about the instantaneous values here. So that's what I gather, because it says its magnitude is the intensity of light. It's normally the magnitude of the average value of the Poynting vector is what we should consider, but because it's stated like that in the problem, I did not put a factor of 2 here. So normally we should put a factor of 2. So this would be square root 2I mu 0 C, for example, when we consider the average value. But this is not, here the intensity is not defined as the average value of the Poynting vector magnitude. That's what is given in the hint of the problem. Okay, so we have used Faraday's law to calculate epsilon, and we compared to the answer for part A to get the BE relationship. B is equal to E over C. We can write a right circularly polarized and left circularly polarized wave by changing the sign in front of the sine function. So that's what I have done. By adding the right and left circularly polarized waves, we obtain a linearly polarized wave as suggested. If I consider a green light, lambda is equal to 500 nanometers, intensity 100 watts per meter square, the 1 over mu 0 E cross B gives me the Poynting vector, which is EB over mu 0 k hat. The magnitude of the Poynting vector is EB over mu 0. And E is equal to B times C, so B squared C over mu 0. So B is square root I over mu 0 C, E is square root I mu 0 C. From this, substituting the numbers, we obtain our final answer.